So it is a pleasure for us to have Professor Mary Hayhoe with us today in our Bar-Ilan University Vision Science Seminar. Mary Hayhoe is a professor in the psychology department and the Center for Perceptual Systems at the University of Texas at Austin. She did her BSc in psychology with a minor in math at the University of Queensland, Australia, and a PhD in psychology at the University of California at San Diego. She then moved to the University of Rochester's Center for Visual Science, where she was an associate director of the center for almost a decade and a director of the cognitive science program for even a longer period. After that, she moved to the University of Texas at Austin, where she's now located. She is recognized for her work in eye movements, attention, and working memory, particularly in natural tasks and environments. She has pioneered the use of eye tracking in virtual environments for the investigation of naturally visually guided behavior in controlled settings. She was the president of the VSS for a couple of years and also on its board of directors for several years. She served on the NIH Visual Sciences B study section, is a fellow of the Optical Society, is on the editorial board of the Journal of Vision Science, and served as an associate editor in perception and psychophysics for many additional committees and panels. She received the prestigious VSS Davida Teller Award among additional awards and honors. Her research is continuously funded by multiple funding bodies. She's the holder of a patent and published many original research papers and reviews in high-profile journals, including Science, Trends in Cognitive Sciences, Current Biology, Annual Review of Vision Science, J Neuroscience, and others. She also published several books and book chapters. Her research started off with investigations of visual sensitivity, adaptation, and color vision, and nowadays concerns the functioning of vision and visually guided behavior in the natural world. She uses eye tracking in both real and virtual environments to reveal the mechanisms that control allocation of attention in natural context and the role of working memory in visually guided behavior. She's interested particularly in the role of reward mechanisms, stimulus uncertainty, and learned priors in control of gaze. And without further ado, I'd like to welcome you, Mary, to our seminar. Thanks so much for joining us.
Thank you, Sharon. That all sounds quite exhausting. I was like,
sorry.
Oh. All right, no, let's see. Okay, I'm going to share my screen, and here we go. Present a view. Well, good morning. Well, good evening, afternoon, everybody, and thanks for joining me in this talk. And so I'm going to talk about visual decisions in natural action with my collaborators Carl Muller, Dan Panfili, John Mathis, and Kate Barnum. So first of all, I'd just like to motivate why would we do something crazy like study natural behavior. And I just sort of want to say what's different about this from our standard experimental paradigms where we're sort of manipulating something and getting a particular judgment out of the subject. And so the big thing is that in natural behavior, you're basically deciding what you want to do. And so your eye movements, where you're walking, et cetera, et cetera, et cetera. These are decisions you make. And there's this continue, you're going from one thing to the next, and nobody's sort of controlling that, you're controlling it. So that's something that's hard to get at in standard experiments. Another sort of simple thing is, like, particularly with eye tracking, when the head is often fixed in space, you just can't do very much, it's the repertoire of behaviors is really kind of limited. But when you're looking at natural behavior, you're just moving all the time, even when you're trying to stay still, those small movements. And this is generating a kind of complex and rather unpredictable sequence of stimuli on the retina. And this is the kind of thing that I'm going to be focusing on today. And also this issue of what gets you from one action to the next. Okay. So just to give you an example of this is John Mathis walking across the road, and this is something we do. It's pretty easy. And so the crosshair shows you the gaze, and you can see your eyes jumping around all the time, and it all looks very busy. So what's controlling this process? And so let's look at it. You look at the curb, the walker wants to pass the girls, he looks and figures out where they're walking. How does he have to control his body to get around them? Maybe there are other pedestrians he wants to avoid, and so on. And so we really need to understand this, what is determining where gaze goes next, and how is this controlling your walking decisions. And so just a little timeout. So for those who perhaps less familiar with the terminology, although I'm sure you're all very familiar, the periods when you're holding gaze fixed in the world for a little while, that's the fixation. And then most of your eye movements in this kind of situation are these high velocity stochastic eye movements where you jump from one location to the next. Okay, so I'll probably use that language. But if you think about, okay, this is vision, this is what the visual system has to do. And so what do we need to know? And there are kind of two things that I've been focusing on is, so during a fixation when the eye is relatively steady, what's the information you're getting? So presumably when you look at the curb, you don't want to trip over it, right? And so you have to program an appropriate stepping movement so you don't trip. And so when you've got that information, say you looked at the girls, what information do you need? You need to know how fast are they walking, what direction are they walking, and you have to predict what their trajectory will be so you can plan your own trajectory. So what's the information? How is it being used in decisions? I'd just like to give this kind of context for thinking about it, which helps me and maybe I hope helps you organize all these thoughts. And so in recent years, people think about these action decisions in the context of Bayesian decision theory. And so we need to get information about the state of the world. So we get noisy sensory data. And then there's the supplemented by our priors, our understanding of the state of the world. So for example, on streets, there will be pedestrians. So you need to take that into account. But pedestrians also tend to walk in fairly stable directions. So you can use your prior about pedestrian behavior and to estimate the state of the world. And you also need to take into account things like what's the cost of bumping into a pedestrian. That's a smaller cost than bumping into a bicycle, and so on. And so all of these factors are going on at this time scale of a few hundred milliseconds that lead to decisions about where to walk, where to look next, and so on. And so this I find a useful framework, and we'll come back to it. Okay. I'll come back to it if I could advance my slides. There we go. I'm going to talk, I'm going to address two questions. Okay. And the first one is how these movements actually shape the visual input. This is important because we need to know what the actual image statistics are that's getting into the visual system, because these are the things that shape the structure of vision. The second part of the talk, somewhat a little different focus, which is we want to reconstruct the terrain. So if we don't know exactly what the image is that you're seeing, you can't kind of figure out what the visual information is that you're using. Okay, and so two parts. So this is what we're doing. Just it's the eye movements, binocular eye movements in this case, and we're tracking the body. It's a little hard to see, but this is a motion shadow inertial measurement unit full body motion capture. We have a couple of data sets. This was one set was collected by Kate Bonin in Berkeley, and then we also have some data from Austin collected by Carl Mueller and John Mathis. Okay, so what do we get? Okay, first of all, look in the top right here. This is the subject's, the walker's point of view, and you can see where they're looking. It all happens rather quickly. There's a camera mounted on the head, and so you can see they're looking at basically where their feet are going to go. Down on the bottom left here, we have this little stick figure. This is the integrated data from gaze and body, and the little spots on the ground are where the feet are going to be going. The important thing is up on the top left here, what we do is we align the images so that they're all centered on the fovea. And so this top left thing this is what the visual system is getting. It's not getting the stuff from the head camera, it's getting the retinal centered viewpoint. Okay, now I just like you to look at this is the eye and head trace in the bottom right here. And you can see you're making these high velocity saccadic jumps and then holding gaze relatively stable as the body moves forward. So just to illustrate this, give us a sense, because it's important. You have a fixation on a rock here. This is actually a lousy image, I'm sorry, but make a saccade to the next rock. And while the body is moving forward, as you can see over on right here, so the body's moving forward, gaze is fixed in the world, and the body is kind of rotating around this fixed gaze point. Just to see what's happening, this is the eye and head now, and so you see these are these high velocity saccadic movements from one location to the next. And then in order to maintain gaze, mostly vestibular ocular reflex is stabilizing gaze while the body moves around, and we go on to the next one. And so this is basically what you do when you're walking. Now we're going to look at the effect of the terrain. And so in rough terrain, you need to look where your feet are going. And so you're mostly looking down like this. On the smooth paths, you're looking up and around. You tend not to look close to your body because you just don't need that information for footholds. And so what happens? So the interesting thing is that this sort of vertical gaze angle is very sensitive to the terrain that you're in. Over here on the left, these are these low angles. You're looking down very close to the body. On the right of the plot, you're elevating gaze angle to the distance. And so this yellow histogram here shows the gaze angles when you're walking on pavement. Interestingly, a flat path, which is now just regular dirt, you still look in the distance a lot, but you're spending more time looking closer to the body. And then in the rocky terrain, you're pretty much centering around a few steps ahead. So you can see that the needs of rocky terrain are going to be different. And so the task is controlling the gaze distributions. The gaze distributions in turn determine the retinal input. And that's what I'm going to go on to next to show you. So let's come back to our little decision plot and think about what's going on. So on the flat ground, you can just use some prior that we know it's flat, it's not going to change. As long as there's no big rock in the middle of the road, everything's fine. You don't really need to get new visual information. You can use your prior. In the rocky terrain, you've got to have more visual data as the ground is getting rougher. So we have to add in that factor. And so that's why you're getting more looks to the ground. But it's also more important, you need to find stable footholds, and so the cost function changes. And so it all works out rather beautifully. And so now we're going to focus on how the retinal input is affected by the gaze behavior. There are two factors to think about. And so, and this is why I focused on this saccade fixate pattern, is that while gaze is fixed on the ground, what's happening on the retina is the ground plane is rotating forwards like this, top forwards, and it's also expanding. Okay, so that's the way it's changing the retinal input. And then the other thing is that the body is kind of sways during the gaze cycle. You're not just translating on its fixed layer trajectory. The head is swaying left and right, up and down, and there's forwards, backwards movement too. And so this confers rotational components on the motion on the retina. So first of all, this is the map of the speeds across the retina, to plus or minus 45 degrees. And so these are sort of equal speed contours here that we've got. The dark blue says that it's very low speed, and that's because where you're fixating, there's actually no motion or very little motion. And so you can see that the distribution of speeds is in this region, peaks at just a few degrees per second. As you go to the upper visual field, you're getting these, the velocities are, the speeds are increasing. And then close to your body, because the ground is close to your body, you're getting the highest speeds there. So the distribution here is speaking about 20 degrees per second. So you get, even when you average all the data out, you're getting this marked asymmetry between upper and lower visual field. And this is just a consequence of the ground plane. We always have a ground plane with us, so we could expect that this kind of lower visual field asymmetry is going to be a sort of feature of a lot of the visual input, motion input that you're getting. And then again, because of the fixation location, this plane is kind of tilting around that. And so you get this sort of sway of sort of you're not changing velocity very rapidly in this left-right direction. So now what we're going to do is we're going to separate out that data by the visual angle. So at the top, you're looking at the distance, and the bottom, you're looking near your feet. And so here on the right, you see how this vertical, the upper lower visual field asymmetry changes as the gaze angle changes, and it's less extreme when you're looking close to your body, more extreme. And so this would be your sort of, this top one, this would be average walking around in your house or on paths and things like that. So what can we make of all this? First, so we've just talked about these kinds of asymmetries that we might be expect to see reflected in the structure of the visual system and our motion sensitivity. We've dealt with the effect of vertical gaze angle. Whoops. Now we're going to talk about the effect of gait and how that modulates the motion patterns. Now, this next slide, this is really complicated when I start the movie, so don't freak out, okay? I'm going to take you through it step by step. First of all, I want you to look at this, and when I start the movie, this will show you the flow patterns on the retina. And down on the bottom right, when I direct your attention there, you can see our little stick figure and this gaze vector. This is where you're looking on the ground, and this vector is the momentary direction of the body. So let's get this going. And so you can see that these lines up in the top, so you can see this sort of spidery pattern wriggling around, and it's sort of the rotational component is changing. And so on the left, we have the rotational components, and you can see that here gaze is fixed on the ground during the fixations, and you can see that white vector, it's sort of rotating systematically. Similarly, for the expansive component of the motion, you can see that the expansion is modulating systematically. You can see the pink vector is gaze on the ground, and the white vector is momentary direction of the body. So you generate these very systematic transformations of the image while you're walking. And so it seems likely that since you spend a lot of time walking, that you become very familiar with these patterns that you generate by your own body motion. And everyone has slightly different gait patterns, so one might expect that you would be able to learn these patterns. And so why is that important? Just to skip here, just a summary that if you are learning those statistics, there are a couple of ways you can use that. So for example, it's likely to be important for controlling your posture through the gait cycle. And so you learn what kind of motion is consistent with stable walking. And if suddenly you've got some weird velocity vectors on one side, maybe you're falling. And so indeed, there's actually quite a lot of evidence that modulating flow fields will modulate posture, and in trained gait, that's a lot of work. Bill Warren has done a lot of this, and so it's a very profoundly important piece of information, probably for posture. Another reason that this might be important is that one of the fundamental problems of the visual system is to discriminate between motion that you cause yourself and motion in the real world. And so if you know very well what the motion is that you caused, then you can, perhaps this is an important factor in making this discrimination between motion out there and motion that you caused. And this is, all animals have to solve this problem. And then just to reiterate, the first part of this was that the upper lower visual field asymmetry together with the rotational component, these profound effects on the, even though you're fixating and your body is moving, you're generating these motions. And so we can see that you can't really understand the visual input unless you understand exactly what the momentary behavioral goals are. And why is this interesting is we should be able to look at MT-MST and we maybe have a better description of the sensitivity. We may be able to have to sculpt the stimuli so that we can look at the tuning patterns of the cortical neurons in a slightly different way. So that's part one of the talk. And I'm going to now move on to the issue of how walkers make foothold decisions. Now, here we have this movie. I realize it's a bit jokey, but believe me, this little walker is just hopping along just fine. And so here's our problem. I don't know, maybe half a second, a little longer. And within that period, you have to get the visual information, maybe with 1 or 2 or 3 fixations even, and find good places for the foot to go. And there are a lot of things that you might need to be taking into account as well. You need a stable footholds. You don't want to fall. You want to conserve energy. You want the most efficient gait. You need to do all this very quickly, as I said. And you also need to know what the noisiness of your own body is, the noisiness of your sensory systems. And so you need to take that into account in controlling how conservative your decisions are. All right. Now, does it make sense to even try and predict footholds? Maybe they're totally random and it's a lost cause. So this is sort of encouraging. And so here, we've got two different subjects, red and blue. And you can see here that on the left that the walkers are all choosing a pretty much similar part of the walk, except their own visual motor systems. And each walker takes, like here there are 3 different paths. So you can see that walkers off in a point of convergence here, like everyone is choosing this as a good place to walk. Even when they diverge, there's also some commonality. So here the different subjects all choose this different path here. Over here, where paths are diverging more, but again, the 2 subjects both think this is not a bad place to walk, but you can see from here that there's a certain level of flexibility. So we shouldn't expect to do perfectly at predicting footholds, but we should be able to find some of the things that are leading to these regularities. Just again, now thinking what's the problem we're dealing with, we're sort of looking at everything all at once. It seems likely that for a certain level of complexity of terrain, you need to set some parameters, say like walking speed, that's consistent with your learned representation of terrains like this. You need much better sensory data. So this is, that's kind of what we want to know. What is that data? We'd like to also know a little bit more about this cost function and how is it modulating gait. And as I mentioned, this has been a lot of work on how the dopaminergic reward circuits modulate these sensory decisions on this sort of very rapid time scale. So what do we know about locomotion? So we don't really know a whole lot about how vision controls walking. That's because a lot of the work is done on treadmills or flat surfaces. And so this, the visual input is relatively unexplored. We do know that when people are on flat surfaces, they naturally adopt what's called a preferred gait. And excuse me, this is a gait that takes advantage of the passive dynamics of the body. And so you're this inverted pendulum. And so if you walk at a rate that's consistent with your own passive dynamics, this minimizes your energetic expenditure. But in these situations where it's flat, you can really control gait with, maybe low-level pattern generators can control gait. And you don't need visual input, but how is visual input getting in there? So that's a lot of work by John Mathis and Brett Fixation, a series of interesting papers. And they showed that if you want to take advantage of this is the inverted pendulum motion of the body. If you want to take advantage of this passive dynamics, you need information from at least 2 steps ahead. And that's because if you have to brake at the last minute or you have to change your direction, that's going to cost you. You're messing with your inverted pendulum. So we do know that. But now, once we get into these complex terrains, what can we learn about visual control? And what we're going to look at here is where are they looking and what information is being used for this foothold choice. And just, we're not going to solve this problem, but we're going to learn something. Okay. So what I spoke to you about in the first half of the talk, we just assumed a flat ground plane. And you can see it's not flat. It's very complicated, and this is going to add complexity to the visual input. So the first thing we want to do is try and get a better representation of the ground plane. So instead of having this flat ground plane, we'd like to know, okay, what exactly is there? And you can see you get a bunch of parallax errors, so you're making wrong estimates about both the feet and gaze location with that. And so once you have this terrain representation, you can do a lot better job. And so the way that we do this is to use what's a procedure called photogrammetry to recover both the 3D structure of the terrain and also the path of the scene camera through it. And there's quite a lot of work in this in computer vision, and for the most part, it works pretty well. And so when we do this, and the basic idea is, as you can imagine, structure for motion is going to be an important way that you can do this with a moving camera. You can reconstruct the terrain from fundamentally the structure for motion information. And so here now you can see that you don't always look at exactly where the path is. You're checking out neighboring regions. You have to select a path. But for the most part, you're looking fairly close to where the feet are going to go. All right. So why are we doing this? As I kind of pointed out, so now we can analyze the image at the gaze point, and this allows us, and because we've got more accurate data, we get better information about that. And so by understanding the actual terrain structure, we can ask, what's the visual information you're getting? So first of all, we just want to make sure that you are you really looking for footsteps? And so this says what we're doing is not entirely crazy. So what this is so the little guy here is looking ahead, and the gaze is centered around the nearby footsteps. This is step n+1. You're currently on step n. This is the planted foot. And so you can see you're actually spending most time on n+3, quite a bit of time on n+2, n+4. Actually, this n+5 too, we just don't have it in this plot. So the fact that your gaze is clustering around the upcoming footholds is, yes, you're really looking for footholds. So it makes sense to ask these questions. Okay, now how on earth do we figure out what information people are getting? So we just sort of start with some guesses. It's actually a difficult problem, and so we've struggled with it, but here's what we've got so far. So over here on the right, you can see the pink spots are where the person actually walked. But we want to generate some other paths and to say what's special about this pink path. And so to generate random paths, we have to generate feasible random paths. So there's no point in predicting a path for the next step that's longer than the legs. So you have to account for the leg length of the person, and so they can only step a certain distance. So we, for these kind of alternate possible paths, we constrain them to be within the range of step lengths. We also constrain them to be within the range of direction changes that subjects adopt. And we also constrain them to be, there's a certain slopiness that you can't, if something is too steep, your foot will slip. And so you don't step on things that are too slopey. So we generated a bunch of random paths like this, or strictly Kyle generated them. And so what we're looking at here is the average slope. So we're looking actually at these 5-step paths, and we take the average slope along this 5-step distance. And so you can see that the median average slope, the median of this distribution, is it's actually pretty gentle. It's about 9 degrees. This is the distribution for the random paths constrained by walkability. And so you can see that you're tending to choose less slopey paths, although of course it's a fair bit of overlap with the distributions. Okay, this is slightly different look at things. So here, what we're doing is say, let's suppose you're here and you end up here. These are, say, two steps, 5 steps apart. Now, why didn't you go straight? So we look at the the mean slope if you walk straight for these 5 steps, and then we look at the actual chosen path. So often you would choose a more circuitous path. So this, in the literature, this is called tortuosity, and so I'm going to call it curviness or circuitousness. It's hard to find good words here, but so what we're doing is we're taking the mean slope here for the straight path and the curviness of the chosen path, and so you can see they're pretty tightly correlated. This is just one subject here, and so as it gets more irregular to get these along these 5 steps, then you're much more likely to choose a longer way around. So that was one subject. And so here we have, there's a total of 9 subjects. And so you can see that this correlation is holding pretty well for all the subjects, although the slope of the line is a little different. And so what we do in the next slide is what we're plotting here is leg length on the x-axis, and this is the correlation coefficient between of those plots. Between this is your trade-off between slopiness and curviness. Okay, and so here are the little people. This is where I would be, and we had like people over 6 foot, and so we're with very long legs, and so they're have a less tight they still have a correlation, but it's less tight. So the way you position yourself on this trade-off between height changes and circuitous paths depends on your leg length and maybe some other things, but that we haven't found out. But it's very lawful. So one more thing. And now, let me just stop this for a moment. It's a bit distracting. So these analyses that we've been looking at is basically we've been putting in this mesh or this 3D reconstruction of the path, but we actually haven't been accounting for the observer's point of view. So these videos are taken from the viewpoint of the walker, and so this is what the walker sees. Is but again, it's the 3D reconstruction. And so what we're doing is we're throwing this into a neural network and we're giving it a whole bunch of we're giving it paths where we identify the actual footsteps, and we're seeing if the network can learn what are good places to walk, okay, given this view. And so it's quite a big, it's about 45 degrees field of view. And so the dark splotches are where the network has learned are good places to put your foot. So you can see it's not doing too badly. So of course we train it on a bunch of data and then get it to predict the footholds in in the untrained thing. And so, whoops, sorry, that's, okay. So this is what I want to show you here. So here you can see that, so we use this area under the curve thing for basically, which measures the extent of the coincidence between the actual footholds and the predicted locations for the footholds. So here you're doing pretty well, but on the left here, obviously not so well. People walked here, and this is the model predictions. But if you look over 9 subjects here, these little dots is somebody up here. This would be chance performance, 50%. And you can see we're getting about 70-75% of the area under the curve, which is it'd be sort of like a D prime of, I don't know, 1 or 2 or something rather. Actually, I just made that up, but it's kind of, it's not bad, but not perfect. And so what can we conclude from this is there is something in the terrain structure, 3D structure, which is allows you to do a decent job of predicting places that would be good to walk. Okay. Okay, where am I now? I'm trying to find my cursor, and there we go. So what do we know? So we know now that subjects are avoiding nearby paths or steps that involve big height changes. The height changes are energetically costly. So it's clear that on this step-by-step basis here, you're really concerned with minimizing energetic costs. And it's a little hard to tease out stability. Also, you don't want to be stepping up and down because that is challenging your stability as well. And so it's hard to tease out those different factors with what we've done. But it would be nice to be able to do that. The other conclusion from this is that you're trading off the cost of height changes with the cost. So if you're doing a more circuitous path, that also costs you. And so there's going to be some trade-off. It would be kind of nice to actually quantitatively compare the kind of trade-offs that people make. And if that might be a way of getting stability out of there. And another thing, I didn't actually give you the reasoning for this, but with other analyses, it's clear that you're not just planning 1 step ahead or 2 steps ahead, but you really seem to be planning over at least a window of about 5 steps. And so you're adopting some kind of either, reasonably long-term or medium-term policies about where you should be going. And so the planning is taking into account your future, maybe 10 seconds ahead or something like that. Okay. So I'm winding up here, and so just to step back and think about this and summarize everything. So if we want to understand determinants of gaze and walking, we need to really know what's the information you need. So what are these little tasks that you need to do? What's the information that you're using for those tasks? And when you do that, you have some leverage on why are you choosing the next step, the next gaze location. We've also demonstrated the importance of, just on a step-by-step basis, the importance of the neural reward machinery in controlling moment reactions. We've also looked at the importance of the body and figured out just exactly what is the motion, the statistics of the motion patterns on the retina. and how they vary with the behavioral goals of the walker. And again, I think this is important because when you know how the motion patterns are varying, this allows you perhaps to sculpt stimuli in a slightly different way for determining the neural tuning in motion sensitive areas, which is quite complex. And now finally, just to thank my collaborators, John Mathis, who started all this line of work, Kate Bonin, who collected lots of data, and Carl Mueller, who did a lot of the work in the footsteps, and Dan Panfili, who's also doing a lot of the analysis of the gaze patterns. That's all I got for you. So it's open to questions.
Thank you very much for a wonderful and fascinating talk. And I'd like to invite everybody, first of all, to unmute yourselves and let's give a big applaud. It's really fascinating. And I'm opening the stage for questions. I've got a few of my own, but I'll let the others, others ask first. And then I'll join.
Okay.
Jeremy.
That was gorgeous. Coolest graphics I've seen in a long time for starters. But I'm wondering about errors. If you, I don't know if you have a body of error data, but if you look in the wrong place, do you put your foot in the wrong place? If you make an error, is it clear that you have collected the wrong information? What do you know about errors?
Well, one thing is that people actually don't make them, or are actually pretty good at walking. And so what you do make is this is something we need to look at in the eye movement data. You do look in the wrong place. And so you see lots of places where the eye will go off here, and then you'll change. You decide that's not a good place to walk, and you do. So I think what you do is you modulate your speed, and so there's this very tight modulation of speed with a terrain complexity, and we actually have some measures of that. But so you avoid errors by slowing down, so to give your visual system enough time to figure out its main mistakes. And so at one point I wanted to look at the places where you looked and didn't walk and compare it to places where you looked and did walk, but we couldn't make that work. But yeah, it's an important question, and I would desperately love to know more about that, how, but I think it's mostly you manage to catch your errors before you make them. We don't like to fall over. You always slow down. So, thanks.
Frank, would you like to, Frank Bremer?
Yeah, Mary, thanks a lot. That was a really great talk and great data, I think, and really appreciate that. So I have a question concerning the first half of your presentation. I'm not sure, am I right that it was kind of void of saccades, so that it was, or yeah. I put it differently, do you have any idea about the role of saccades?
So what we did is we just took the motion, we actually cheated a bit. I'm gonna put this up here. And we assumed that the eye is perfectly stationary. It's not perfectly stationary. There is a little bit of slippage, but we just ignored it. It's actually shocked. I was shocked at this. Mostly this is like so the mode here is 1/4 of a degree of slippage, and even the median is less than a degree. So we figured we'd ignore that because we actually have looked at that, and it does modify the motion patterns a little bit. But we didn't, sorry. We also looked at the motion generated by the saccades. And if I had been a better person, I would have had that plot, but I don't. So we have that separately.
Okay.
The reason we did this is that we know that the reason you stabilize gaze is that's when you're getting the information. And so the saccades will definitely give you this big transient. And since we don't really understand all that well what the visual system is doing with the saccades, although there's some recent work by Daniel Butts, which says that V1 is doing a suppression right at the onset and then a subsequent enhancement. So we have this, we have actually the three things. If it were perfectly stationary with the retinal slip and with the saccades, but I think it's important to break it down. And the other thing we haven't accounted for here, which we're starting to work on, is what's the structure from the complex terrain. You've got noisy motion added onto that, right? And it is interesting that the amount of complexity, the amount of motion energy added is from the rocky terrain actually sort of correlates with the speed of walking. So you're sort of taking that into account. So yeah, so I just chose to keep them in separate boxes.
Okay, thanks.
Okay.
Oh, wonderful. Jan and Oliver?
Mary, Rachel, I have a question about the first part, which is you showed this quite alarmingly complex set of rotations that take place in the course of a stride. And you suggested that we learned those patterns and could discount them. But presumably we're also getting information, highly relevant information from proprioception and vestibular sense about how our head is moving. And can we use that to?
Oh, totally. Yeah, I'm sure. You know, I think though that usually vision wins over vestibular information, but yeah, for sure the proprioception is working because apparently there are these little spinal modulators of the gain of the vestibulo-ocular reflex. So it's really complicated, and I wouldn't even pretend to understand it. But yes, I'm sure you have some. So you know, presumably your expectations when you're running are going to be different from when you're walking, and yeah. So it would be really. I kind of think though that vision is. It's probably a bit more sensitive, and the fact that there are these studies which show, you know, you can stand in front of a screen and it's expanding and contracting, and your butt is doing this, right? So even when there's no other proprioceptive input, you know, so it does seem to be quite powerful, and so that's the next thing. I think it, yeah, so there's a whole bunch of experiments. Yeah, most of this is like, I'm making these wild claims. It's just observational data. So we're just making guesses. And so all of these things need to be studied as you point out.
Can I just ask you whether you have any data that you can analyze, which is relating the foot size to the rock size?
One suspects that foot size and leg length are correlated, so, but we haven't separated them out. But interesting, yeah. You know, I don't know. There's enough flexibility in possible paths that it might be hard to tell. But yeah, not yet. I mean, I think we just got this one modulator, which is leg length, and I'm sure there are others.
Okay.
Lovely. Crystal, would you like to ask?
Sure. Hi, Mary.
Hey, Crystal.
It's great to see you and hear this wonderful work, as always. I have a question for you about driving. So does using an implement for navigation, which eliminates foot placement and all this bodily movement, does it actually simplify what the visual system has to do in terms of processing? Or does it just change?
Yeah, totally. Yeah, and this is anything I said. It's just really doing with walking. But yeah, if you're at a constant velocity, you know, then basically the Gibsonian picture is much more appropriate. You know, if you're translating in a constant direction, constant velocity, yeah, it makes it a lot simpler, I think. So I haven't really thought too much about it, but you know, it may be that you use the flow patterns in a different way when you're constant velocity, you know, constant direction like that, and don't have the wiggling around and stuff. Although, I mean, it's hard to hold your eye completely still.
And you don't, right? When you're
Your head wiggles, right?
Mm-hmm.
And there is also, depending on the luxurious nature of your car, you also have some motion from the car, but it is a much simpler situation for sure.
Okay, thank you.
Yep.
Wonderful. I myself have a question about, first of all, if there's any contribution of stereo vision, because when you walk, especially in the next first or second steps ahead, stereopsis, I guess, would play an important role. And what do you think would be its contribution to determining, or I don't know, even the variance or the noise in your walking and in your planning, especially in such non-uniform terrains?
Yep. And again, if I'd been a better person, I'd have a slide for this, but Kate Bonin, that was Kate's project. And so, and she was doing binocular tracking, and we compared binocular and monocular. Shockingly, it didn't make a huge difference, but what you do is you look a little closer. And so, which says there's a bit more uncertainty and you're getting better information. So yes, you use it. And I would say that's an unexplored question, is basically how much is stereo, how much is structure from motion? And that's something that we need to work on, but yes, stereo matters. But there are some kind of interesting little hints there that we haven't gone into, mostly because we don't have good enough data. But Kate said that the people who had embryo, we actually looked at some embryos, and she says that their feet slap on the ground. So it may be that they have a slightly less good estimate of the actual depth of, you know, the ground. So I think there's stuff to do there. Yeah. So we did both amblyopes and monocular, binocular. But yeah, that seems to be your general thing. The more uncertain you get, the closer you look to the body and the more you slow down. And so you regulate. I think that's how you stay within that's how you avoid the errors, Jeremy. You stay within, you know, what your limits are. And I think that's kind of interesting, because it really means that you know how noisy your system is. It's really amazing. So.
Thank you. Jan and Olive, again.
Yeah, Mary, in that context, one thing you didn't say an awful lot about, but seems rather critical, is that the local gradient of the rock where you're planning to put your next foot. That is must be one of the prime things in choosing the foot placement. And that would be something where stereo would be quite helpful as to whether you're going on going to have a horizontal little bit of rock or a 30-degree bit of rock.
So Carl went into the literature and he found people have looked at stepability, the slope that you can step on, and it goes up to about 30 degrees. You will not step on anything less than that, more than that, sorry. So he included that as a factor in the predictions for the random slope. So that was included in the comparisons. It's like all those non-steppable places were ruled out of the prediction. So, yeah.
The
Yeah,
question is, where are you getting that local slant information from, do you think?
I don't know, but you're getting it. And so clearly it must be stereo, presumably motion parallax too. So it would be, it always seems that stereo is better than motion parallax, which sort of surprises me. And I would like to kind of get a better sense of how important motion parallax is in this, but we haven't really gone into that yet. So,
Mary, may I ask another question?
of course.
I wanted to ask about the different areas in the visual field where people may be looking at. I mean, there's different motion trajectories during the optic flow, and I wonder when usually people are looking 1, 2, 3 steps ahead, are they looking at the top of, well, I assume it's at the top of the visual field, but do you think there are areas that are more informative, say, let's say the central, less, right and left, more the central trajectory or their visual field, or different weights?
I didn't show this, but so what people actually do is, even in the rocky terrain, they'll be spending a lot of time looking at the ground, but every now and again you'll see a look up in the distance. So it's kind of like you got two jobs. It's like, am I going in generally where I want to go? And what's it like up there? Or is there a big obstacle? We haven't looked at those in detail. For the steps near the body, again, you sort of go maybe 5 steps ahead and then come back to closer. The distributions around the footholds are actually quite symmetrical. So the standard deviation of those distributions is about a 0.2 of a meter. So what that means is you're not looking at the way you put your foot is not really necessarily foveated perfectly, although it centers, the distribution of gaze centers on where the foot goes, but it's got a pretty good size variance. So what that means is a bunch of the time you're getting, the information you're getting is in parafoveal vision. So it's about, say the standard deviation is about 5 degrees of visual angle. So that's gaze around a foothold. So you don't necessarily need perfectly foveal information, and which may be why the effect of stereo was relatively modest. It didn't change walking speed, and a few other parameters like that. But yeah, we did find a correlation between how close to the body you looked and your stereo acuity. So the poorer the stereo acuity, the closer you look to the body. So yeah, it's a bit messy, but you don't actually look. It's kind of like you can pretty easily get. The thing about walking is it's like you don't really need to work too hard to guide your direction. It's kind of like, oh, I'm going up there, pointed that way, and then you make these little modifications. And this may be where you're using your proprioceptive information and vestibular information, and you're so updating where am I with respect to my goal, and so you only need to check on that with every now and again. But they tend not. When the terrain is demanding, you're not looking at the scenery. So you just don't even look anywhere near non-viable paths. So you are clustered within, maybe plus or minus 10 degrees of where you actually walk.
I do have another question, and that relates to individual differences. I mean, I assume that most of the people that you measured vision and their walking is usually probably well-fit young individuals. Maybe I'm wrong, but I'm wondering, I mean, there's big individual differences between the coordination skills and the security that people, or the confidence that people have when they walk on, you know, uncertain terrains. I'm not talking about pavements and sidewalks, but, you know, in nature, some people just almost run and hover over the trails, while some are very, very slow and insecure. And I wonder if this will be evident in the way, not only in the way they walk, but in the way they actually sample and observe the terrain.
I think the answer to that is yes. And so, whereas we're all skilled walkers and to a certain extent, but the distributions of let me just show you this. I need to go way back. Sorry. Oh, here we go. So this is one subject, and so this subject is spending most time at N+3. Now, if you look at how the individuals, and so I think this is rough terrain. If you look at another person, like some people will never look at N+1, okay, and be looking more at N+4. Others you will look more at N+2 than N+3. And then the way that those patterns change with terrain also depends on the subject. But this is something we have not got a handle on yet. And so leg length for sure is going to be involved, right? But yes, like you say, that there are all these other factors. And so I think that, yeah, I was not a subject. I would probably walk a little slower. So
I did not have any, I did not mean to.
No, I mean, that's a lot. There's just a lot of complexity here. And, you know, for example, one of the things is that often, you know, people will, it'll be not a very good place. It might be just the ridge of a rock, but you might plan on going to. So you might be planning a sequence of steps where you can bounce off rocks and things like that. And so, yeah, but I think that the nice thing is having the terrain reconstruction in there allows you to start asking some of those questions.
Okay.
So, yeah.
Thank you very much. It's fascinating, really fascinating work and fascinating future directions.
Yeah, thank you very much for inviting me. It's been great to electronically meet everyone. Bye-bye.
Thank you very much for joining us, and also so early in the morning. Like, I guess you were probably one of the earliest time zones.
You'd have been 6 o'clock. I couldn't have done it. So, all right. Well, it's nice to meet you, and thanks everybody for coming.
Thank you very much for the lovely talk.
Bye-bye.
Thank you, Mary. Thank you.
Bye. Good to see you,
Sharon, for organizing it. Bye.